Hi, so let us start the session. Let me share my screen first. Yeah, Anil, so please let me know if my screen is visible or not.
Yes, sir, visible.
Okay, great, thanks. So this week we were going to start the induction machine, right? So we will start the induction motor and we will go ahead. So let me open this. Yeah, so first thing is an induction motor is a singly excited motor. It does not have any separate field winding. So first thing is it is a singly excited machine. And today what we will see, we will discuss about equivalent circuit of the induction machine and we will solve a couple of problems based on that, and slowly according to the schedule we will go on, right? So uh, let me draw an equivalent circuit of the machine. Okay, so essentially, an induction motor relies for its operation on the induction of voltages and currents in the rotor circuit. Okay, so we apply a supply on the stator of the machine, and induction process happens, and hence the voltage will be induced in the rotor bars of the cage induction motor. And since the cages are sorted among them, so a current will flow, right? But the amount of voltage and amount of current is not independent. It will depend on the relative motion between a stator magnetic field and the rotor of the machine. Okay, so let me first go step by step. Let me draw an equivalent circuit first. So this is the stator resistance. This is leakage inductance or leakage reactance of the stator side. Now there will be some parallel components. One is core loss resistance and other is magnetizing inductance. And since induction process is happening, we want to model it as a transformer. Okay, so this will be like this. E1, ER, and JXR. So JXR is the rotor reactance, again RR. We will break them down. Okay, so eventually we will break it down and we will see what are the impact of each elements on the machine. So this is the transformer model, and of course there will be a turns ratio, right? So N effective, that will be the ratio of total equivalent number of conductors on the rotor side to the total equivalent conductors on the stator side, or number of turns you can also call it. Now, since it is a singly excited machine, hence all the power that will travel from this point all the way to the output. Okay, so that's why it is called singly excited machine. And in this path, there will be some losses, right? So we will also see its loss model or equivalent model, where we will represent each elements with certain amount of power level. Okay, but first we want to break them down, and one important thing we want to understand that uh, its BH characteristics will not be similar to the ideal transformer, because Ideal transformer does not have any air gap, but here an air gap is very essential to operate it either as a motor or generator. So that is one thing, and hence its BH curve will be shallower compared to the transformer model, right? And the very important thing is the rotor, right? This ER, XR, and RR. So if you draw rotor equivalent circuit, ER, JXR, and RR, they are function of, you know, relative speed or relative position between a stator magnetic field and the rotor. Why I am saying so? ER will be equal to S into ER naught. Okay. The higher the slip, the higher amount of EMF will be induced in the rotor. Let us suppose that your rotor speed is equal to the stator magnetic field, means NR is equal to NS. Okay. At that time, slip will be 0, right? And slip will be 0, hence your EMF induced at the rotor side will be 0. And as you increase the relative speed between them, like your rotor and the stator speed is not close, they are further away from each other. At that instant, the quantity by which they are they are not close, that will be proportional to the EMF induced in the machine and the frequency. So one thing is that induced EMF is the proportional to the relative speed between a stator magnetic field and the rotor. Another thing is that frequency in the rotor is also directly proportional to the relative speed. So the frequency of the rotor is also directly proportional to the relative speed. And hence we write it FR is equal to SFS. Okay. And as relative speed is higher, hence current will also be higher, right? Because current in rotor is nothing but, let us denoted by IR, okay, is nothing but SER naught divided by JXR will be JS omega L R. So RR plus JS omega L R. So the higher the relative speed, okay, higher will be slip, and hence your rotor current will be higher, right? So rotor current will also depend on the relative speed between a stator magnetic field and the rotor speed. Okay, I hope this part is clear. Right? And according to this rotor model, we further can simplify it. Right? We can divide it by, S and S. So we divide it on the numerator and denominator by S, and we will end up with ER divided by RR plus RR by S plus J omega LR. Or you can write equal to ER naught divided by RR by S plus JX R naught. Okay. And according to this expression, our equivalent impedance of the rotor, we can write RR by S plus JXR. So let us see one problem based on that. Okay. which will be beneficial in solving this or getting this concept fixed in our mind. Yeah, so before solving the problem, one thing I want to clear here, I want to clarify the loss or power flow diagram of an induction motor. So this is the equivalent circuit of induction motor. Let me copy it. Mhm. Yeah. So this was the transformer equivalent model of the induction machine, and we can club it all, and we can end up with one equivalent circuit like we do in equivalent circuit of the transformer. We can also draw an equivalent circuit of the induction machine. Okay. Right. Yeah. So what we can do, the stator resistance and leakage reactance will be as it is, and we have parallel branch parameters, core loss resistance and magnetizing inductance. And we can refer the rotor side elements to the stator side, right? So it is Jx2 and R2 by S. According to why I am writing R2 by S, because here we have computed equivalent impedance of the rotor side, right? So we can write Jxr plus Rr by S. Hence, I am using X2 and R2 just for the sake of convenient. And this is our phase voltage. So this is per phase equivalent circuit of the induction machine, right? So here,
Sir, here RC and JXM is core loss component.
no, RC is only core loss component, and XM is magnetizing inductance. So do you understand difference between magnetizing inductance and core loss resistance? So
Magnetizing.
see, why does magnetizing impedance or magnetizing reactance comes in the picture? Because there will be some current, right, that will be responsible to establish magnetic field or magnetic flux in the rotor as well as the stator, right? Essentially in the core. Without rated flux, we cannot achieve rated power at the output with the least amount of current, right? So see, there will be some current that will flow from the supply. Let me identify it here, I1. Okay. There will be some current which will flow here. Let me call it IM, right? And some I2. This XM, JXM, the current, magnetizing current, I mu I am calling it. This current will be responsible to establish the rated flux in the core. Responsible to establish rated flux in the core. In transformer also this reactance or impedance or inductance was present, right? because in transformer also we provide some current to maintain rated flux in the core. And this inductance or this reactance JXM will be higher in the induction machine compared to the transformer, as I stated earlier. Why? Can you tell me the reason? Why this XM of transformer or induction machine, XM of induction machine will be, lesser than XM of transformer? Can you tell me the reason?
Air gap, sir.
Yes, exactly. Because of air gap, we have a mandatory air gap in the induction machine. And when air gap introduced in magnetic equivalent circuit, what happens? It increases the reluctance of the machine or reluctance of the equivalent circuit, and hence higher current will be required. Are you getting the reason behind it?
Yes, sir.
Okay, great. And RC is different. RC is how much core loss will be, machine because of the whatever flux in the core and whatever frequency of the machine. So core loss is dependent on the flux and frequency, right? So it denotes this RC denotes if you calculate this branch current IC, IC square RC will give you the core loss of the machine. It is equivalent model. It will not give you the exact value, but it signifies that. Otherwise, if you want to exactly measure the core loss of the machine, you have to do either finite element analysis or you can measure it experimentally. This is the analytical model, IC square RC, which will give you approximate value of the core loss in the machine. So we model core loss resistance with RC. I hope it is clear till now. If any doubt, you can anytime ask.
Yes, sir. For X2 and R2 by S, what these are representing?
Yeah. So R2 by S and X2. So R2 by S is nothing but what amount of power that you are extracting at the shaft, right? So if you break it further, R2 by S in two terms, R2 by S, you can write it like, let me, R2 by S, you can write it like R2 1 minus 1 by S, right? Is it correct? R2 S minus 1 by S. Okay, is equal to R2 minus R2 by, no, it is not correct. So, it is broken into two parts. Let me see what are they. So basically, this R2 by S, just right now I derived it here, RR by S. This is equivalent circuit which determines whatever the output power at whatever the mechanical power at the shaft. But generally, we break it into two parts, and one part gives you the copper loss, and other part gives you the output power. Okay, so there are two kind of output power generally in induction machine we are concerned with, right? So let me break it again. This R2 1 minus S by S. So now I think it is fine. Yeah. So if you further solve it plus R2. Yeah. Now it will give you equal to R2 by S. So this component, if you multiply both side by I2 square, okay, and I2 square here also. So this is the standard copper loss expression, right? So it is the rotor copper loss. Okay. And this is known as the power conversion or converted power. Okay, so there will be a power at air gap. One power you are supplying at input, one power after a stator copper loss. There will be one a stator core loss and copper loss. There will be one power at air gap, which we call air gap power. And after air gap power, there will be again some rotor copper loss and core loss. After that, all those losses, there will be one power that will be left that we know as converted power. And after this converted power, there will be frictional and windage losses. And at the end, we get the set power. So let me model it once again. It will be very confusing for you. So let me model it or let me draw a power flow diagram of the induction machine. So it will be clarified. So we are providing input power. Okay. There will be a stator copper loss, core loss plus copper loss. And after this stage, we have air gap power. Okay. So this much power will be induced at this stage. Okay. At this stage. This is the air gap power. Okay. And after this point, what we will have rotor copper loss and core loss. And this stage will be called as a converted power. Okay. And after this point, there will be some frictional and windage losses. And after all these losses, we will get the output or shaft power. That will be load torque into rotor speed. And converted power will be this converted power will be torque induced into omega rotor or omega n, we can say. So one problem we will solve based on this, and hence it will be clarified. But even here, any doubt is there, we can clarify it. Okay, so after certain losses, we have different powers, and that terminologies are very important because what power is asked in the question and what we calculate. Sometimes they may vary. Okay, so it is very important to know them. So, is there any doubt in this, Anil?
No, sir. Clear, sir.
Okay, great, thanks. So let me solve a question based on losses only. Okay, a 480 volt, 60 hertz, 50 HP, three phase induction motor. Okay, it is drawing 60 amps of current at 0.85 lagging power factor. Okay, a stator copper losses are 2 kilowatt, and rotor copper losses are 700 watt. Okay, and frictional and windage losses are 600 watts, and total core losses are 1800 watt. And you can neglect the stray losses. First thing is that we have to find out air gap power. So at this instant, right, this air gap power after a stator core loss and copper losses. And if collective core losses are given, you can include even rotor copper losses here. So total core loss you can include at this stage. Just like in this problem, collective core losses are provided, right? Because you cannot segregate between a stator core loss and a rotor core loss. Now we are given with the current, okay? So we can, first thing we need to identify what will be the input power. Then only we can reduce current from that expression. So first we can calculate input power. That will be root 3 VL IL cos phi. Okay. So VL is given 480 volt. You can see IL is also given 60 amps and cos phi is 0.85. So if you calculate it, you will get 42.4 kilowatt. So that much of input power at this particular current and particular power factor you will get. Now, from the power flow diagram, we want air gap power. Okay. So we have to reduce a stator core loss and copper loss. And in this problem, total core loss is provided, so we can reduce that. So air gap power will be P input minus P copper loss of a stator minus P core loss. Okay. So input is 42.4. Copper loss of a stator is given 2 kilowatt. Core loss is also given 1.8 kilowatt. So you will get 40.4, 40.4, 38.6 kilowatt is the air gap power. Okay. Now in part B, we have calculated air gap power. Now we want to calculate converted power. How much power will be converted? We represent it with. So again, we can take the reference of our power flow diagram. So it will be air gap power minus rotor copper loss. Okay. Or sometimes we call this converted power as mechanical power also. So do not get confused between them. So converted power or mechanical power will be equal to air gap minus P copper loss of rotor. So 38.6 minus total copper loss is 700 watt. It will be 37.9 kilowatt. Okay. Now, since we have calculated air gap power and mechanical power, now we want to calculate output power. So output power will be mechanical power or converted power minus frictional and windage losses, right? From this equivalent circuit or equivalent power flow diagram, we have to reduce frictional and windage losses from that. So it will be 37.9 minus frictional and windage losses as 600 watt. So we will end up with 37.3 kilowatt. So this much power, 37.6 kilowatt of power you will get at the output of the machine. Hence, now we can calculate efficiency of the machine. Output by input. Output is 37.3 and input is 42.4.
Sir,
Yeah.
in A,
Huh.
in question A,
Yeah.
he- here P input minus P copper copper losses stator minus P core losses in stator.
Core losses in a stator. If a stator core losses are provided separately, but that's why I emphasize on this point. If they are not provided separately, you can include rotor core loss or stator core loss, combined core loss at this stage only.
Sir, if node given, then rotor core losses we can include,
Yeah, if
and
rotor
after
core,
that we will find air gap power.
yeah. So if see, there are many approaches in different textbooks. So one approach is that what we concluded that if there are separate core losses are provided, you can calculate rotor core loss after air gap stage, okay, and a stator core loss before air gap stage. If separate core losses are not provided, you can club both of them, or since it is not separated, you can include core loss at this stage only. Is that point clear?
Mm. Yes, sir.
Yeah. So that's what happens. It's a bit tricky thing, but that's how we tackle numerical problems in gate.
But sir, uh, gap power is uh, in air gap of machine.
Huh.
Then stator core loss and stator copper loss
Mhm.
will be considered. But here we consider rotor core loss also.
Sorry, can you repeat this last point, what you stated?
Sir, air gap power means power from stator to rotor in between.
Yeah, in
But
between. Yeah. Huh.
here we also take rotor core losses uh, uh, in stator loss.
Here we took rotor core losses at a stator space. Ideally we should take, rotor core loss after air gap, because, we are moving from a stator to rotor, right? So
Yes, sir.
from a stator core loss and copper loss we can include after we move to air gap. After air gap, there will be rotor core. So in the rotor, there will be rotor core loss and copper loss. So ideally, this should not be here. But since in some authors consider it like you can include all the core losses here at this stage instead of this stage. So I will let you know why. So some authors do not consider at this stage. Instead, they consider it at this stage, and mostly foreign authors they consider like that. The reason behind it, core losses is dependent on flux density level and frequency, right? You agree? Now, flux density and frequency, since induction machine is a singly excited machine, hence it is pre-decided how much you input provided already. So once input is fixed, you can easily identify the core loss from this side. But what some other people can say that, okay, fine, input is fixed. We know the input parameters, but we do not know, or since the rotor side parameters are dependent on rotor current and relative velocity between them. So that flux level or current level or frequency may vary at the rotor side. So they consider it on the rotor side. But you can consider anything, but if in this problem it is already given total core loss, so we do not have any option to segregate between a stator and rotor core loss, so we can consider this approach.
Okay, sir.
Okay, I hope that does not confuse you guys, but that's the reason behind it.
Okay, sir.
Okay, great. So we were calculating efficiency of this motor. So it will come out to be uh, 88%. So 88% efficient this induction machine is. Okay, so I hope this problem would clarify some loss components in the induction machine. And this convert now we can, break this equivalent circuit or equivalent parameters in power and torque components. So this R1 is known as, already, let me get to the circuit. Yeah. So this R1 and I1. So first thing is, you can be directly asked to calculate the current which is flowing in a stator. So I1, that phase current of the induction machine, you can calculate. Since we have drawn the equivalent circuit of the induction machine, you can calculate this. I1 is equal to V phase or V in divided by Z equivalent. And Z equivalent, you can write it like that. R1 plus JX1 plus, you know, uh, R1 plus JX1 plus this RC and XM is in parallel. RC parallel with JXM, okay, and they are parallel with this H2 and R2 dash. So all of them are parallel with R2 by S plus JX2. Right. So on the question to question basis, we will break this whole component, or we can use a Thevenin equivalent circuit as well to simplify this, because this, equivalent circuit broke. To broke this equivalent circuit, we have to, uh, apply a great amount of effort, because they are not just a real quantity. We have imaginary quantities as well. So we will take one problem and we will demonstrate how to go ahead with this kind of circuits. Okay. And core loss, we can directly calculate for any given power. Core loss, we can calculate whatever this E1 that will be induced, this E1, okay. Let me call whatever the voltage that will be induced in the air gap, we will denote that as E1. So core loss will be 3 times E1 square divided by percent. Okay. And since the power, or the power on the air gap, we calculated here in this particular problem, we calculated air gap power from the power flow diagram of the induction machine. But if R2 and S and everything, you can directly calculate as well. You do not need to go from in one stage, initial stage, to the final stage. At any point of time, you can directly calculate it. So air gap power will be 3 times I2 square R2 by S. So whatever the total resistance is available, that will be your air gap power. And this air gap power can be broken into two parts, right? So this air gap power can be broken into two parts: rotor copper loss plus mechanical power or converted power. Okay, so that is why R2 by S is broken into two parts: R2 plus R2 1 minus, sorry, R2 1 by S minus 1. So 3 times I2 square R2 will give you rotor copper loss. And this is just the way of notation, and this notation is very useful when you are solving numerical. So you know that total resistance in the output is R2 by S. That will be total air gap power across this, because whatever input power you have applied and whatever air gap power you are getting, only air gap power has capability to transfer itself to the output. So after the copper loss, reduction in the air gap power, the power you will achieve at the output, that will be your mechanical power or converted power. So let me write it that as well. I2 square R2 1 by S minus 1, it will be P converted or mechanical power, you can call it. Okay, so one thing is this. Now, one another important expression, just to keep it in your mind, that if you are given with air gap power, if you are given with air gap power, what you can do, or even if you are not given with air gap power, you can easily calculate it by calculating the current. So 3I2 square R2 by S. So this is the air gap power, right? And rotor copper loss is what? It is nothing but 3 times I2 square R2. So you can simply write it P S times air gap power. So H time air gap power is nothing but rotor copper loss, and remaining will be your mechanical power. Okay, so these are some important expressions that you can keep it in your mind. And again, if PAG is nothing but rotor copper loss plus converted power, and air gap power is PAG, we can keep it like that, is equal to copper rotor copper loss is SPAG plus P converted. So P converted in terms of air gap and slip, you can write it like 1 minus S into PAG. So S times of air gap power will be your rotor copper loss, and remaining 1 minus S times of air gap power will be mechanical power or converted power. Okay, so these are some important things. Yeah, we were talking about only related to power. Now, when we deal with induction machine, torque components are also very important, right? So which torque is what at what instant, that is also very important. So uh, at the corresponding to this converted power, the torque will be induced torque, right? Induced torque into rotor speed. Induced torque into rotor speed. So if you know the converted power and if you divide it by rotor speed, you will get induced torque. And induced torque is the terminology which denotes the torque generated by internal electric to mechanical power conversion. So at the instant when your electrical to mechanical power conversion is happening in this motor, that will be your induced torque. And this torque differs from the torque actually available at the terminal of the motor. And that difference will be, your losses equivalent to frictional and windage losses. So, okay. One thing is that, but generally you may not be provided with rotor speed. So if you are given with, you can further simplify it like P converted, we can simplify in terms of air gap. So 1 minus F times TAG, and omega r also we can write it as synchronous speed into 1 minus S, right? So this torque also can be equal to air gap power divided by synchronous speed. Okay, so that will be your this induced torque or developed torque, whatever you want to call, or developed torque. So that much torque will be developed or induced. Okay, so there are two ways of denoting your induced torque. One in terms of air gap power, another in terms of mechanical power. And if you will forget, you will definitely forget this expression, or you may get confused. So one thing you can keep it in your mind when you are, calculating induced torque with the respect to mechanical power. At that stage, you remember that with mechanical power or with converted power, your rotor speed will come in picture, and with air gap power, your synchronous speed will come in picture. Okay, so do not mess it up and divide it by different components. So it is very important. Okay, so air gap power directly yields induced torque, and converted power indirectly yields your, induced torque. So that will be another thing to keep it in your mind. Okay, so that is all, and now we can solve one another problem. Okay, so that will clarify all, or that will clear all the confusion between induced torque, load torque, converted power, output power. So we will take one problem to clarify it. So again, for 60 volt, 60 hertz, 4 pole, 25 HP, a star connected induction motor is given, right? And it's all parameters. R1 is 0.641 ohm, and R2 is 0.332 ohm. X1 is 1.106 ohm. X2 is 0.464 ohm. And XM is also given. RC is not given because generally we ignore in big machine. Total rotational losses, and that is another reason that when it is given in the problem total core losses, we generally ignore rotor core losses. And you in many problems you will start to observe that rotor core losses are significantly lower compared to stator core losses. Okay, uh, why? Because a stator is close to the winding, and rotor is far from the winding, and rotor flux density level is generally lower than the stator flux density in induction machine, particularly this cage rotor induction motor. Okay, so total rotational losses are given. 1.1 kilowatt. Okay, and core loss is lumped in with rotational losses, and rotor slip is given 2.2% at the rated voltage. At rated voltage and a rated frequency. Okay, now first thing we have to find out the motor speed. So that is pretty straightforward. Okay, so motor speed will be nothing but ns 1 minus s. Motor speed will be nothing but rotor speed, right? So, and ns we can calculate. Ns is nothing but 120 into f by p, into 1 minus S. So 120 into 60 by 4 into 1 minus 0.022. Okay, so it will come out to be, and inside we can also write synchronous speed. So synchronous speed is nothing but 188.5 radian per second. Okay, and this NR or motor speed is nothing but 184.4 radian per second. Okay, now we need to calculate a stator current. So there are many ways to calculate a stator current, but most convenient is, first you calculate the rotor side parameters Z2, that will be R2 by S plus JX2. Okay, so R2 is given 0.332 and F2 is given 0.464. So it will be 0.332 divided by S is nothing but 0.022 plus JX2, J 0.46. Okay, and it will be in polar form. It will be equal to 15.1 angle 1.76 degree. That will be Z2. Now, another thing is that now we are not given with core loss resistance. So what we can do, we can find one equivalent impedance corresponding to, you know, Z2 and XM. So first we will find out the equivalent circuit and we will call it ZF. This is JXM. So ZF will be Z2 parallel with JXM. So we can write it as like that, 1 divided by 1 by JXM plus 1 by Z. It is nothing but 1 by ZF is equal to 1 by JXM plus 1 by Z2. Okay. Now 1 divided by 1 by JXM. JXM is 26.3 ohm plus 15.1 angle 1.76. Okay, so if you calculate it, what you will get, 12.94 angle 31.1 ohm. So this is ZF. Now, if ZF you have calculated, then it will be straightforward to calculate total impedance. From input side, what you will see, you just need to add a stator impedance plus ZF. So stator impedance is nothing but R1 plus JX1, so 0.641 plus 1.1, 641 plus J 1.106 plus
Sir, what is ZF?
ZF is, equivalent to rotor impedance parallel with magnetizing impedance. ZF is equal to Z2 parallel with JXM. So this parallel branch, this RC is ignored because RC is not provided. In question, it is said that you can ignore RC. So Z2 is nothing but R2 by S plus JX2. So ZF, we are, uh, assigning a parameter which will be equal to Z2 parallel with JXM. Is it fine?
Sir, when core loss component is neglected.
Neglected. Yeah. When that will be there, then you can separately calculate ZC, that will be RC parallel with JXM. And when you have both the parameters, then in that case, it will be Z2 parallel with ZC. Okay.
Okay, sir.
Okay. So this is the stator impedance, and this ZF we calculated 31.1, 12.94 angle 31.1 degree. And you can further calculate it. It is very simple. So what you can do, you can write 14.07, that will be 3.6. Okay, so this will be total impedance that will be seen from the supply side. If you see from the supply side, oh, Z input, this will be Z input, R1, JX1, JXM, JX2, R2 by S, and this impedance is nothing but ZF. Okay, yeah. So this is your Z input. So we were asked to calculate input current. So now we have Z input, we can easily calculate input current in phase, right? So we are given with, since all the equivalent circuit is, you know, single phase equivalent circuit. So this 460 volt is line value, and since it is a star connected, we have to divide it by root 3. So 460 divided by root 3, angle 0, divided by input impedance is 14.07, angle 33.6 degree. So it will be equal to 18.9 angle minus 33.6 degree amps. So we are done with input current. If you are done with input current, you can tell me the power factor of the machine. So that will be nothing but this value only, right? So power factor will be cos 33.6. And it is lagging, of course, because in induction motor, it is rare to have leading power factor. There is no way the machine can operate at leading power factor. Then it will be in generating mode, most probably. So it will be cos 33.6, that will be 0.83 lagging. Now, now we can also calculate input power because we have input voltage and current. So input power will be equal to root 3 VL IL cos phi. So it will be root 3 into 460 into IL, we have calculated 18.9 amps into cos phi 8.833, and it will give us 12.53 kilowatt. Okay. So we have input power. We want to calculate air gap power. Okay. So B part is we want to calculate air gap power. So air gap power is the only thing that you have to take care of, power flow diagram in your mind, or you can directly say that input power minus a stator loss and a stator core loss plus copper loss. Sorry, both. So input power you have calculated 12.53 kilowatt. A stator copper loss is provided. So a stator copper loss is not provided directly. So what you can do, you can calculate it since R1 is provided, right? So we can calculate I1 square R1. So a stator copper loss will be 3 times I1 square R1. So 3 times I1, 3 times I1 is equal to 18.88 or 18.9 amps. Square into R1 is given zero point 0.6 something, 0.641, yeah. So 0.641. So it will be equal to 0.685 kilowatt. So we calculated a stator copper loss that is 0.685 kilowatt. Okay. And in problem, it was said that we can ignore the core losses. So we, we do not need to reduce core losses, so we can ignore it. So that will be your air gap power. Air gap power will be equal to 12.53 minus 0.685. So that will be equal to 11.845 kilowatt. Okay, now we are done with air gap power. Now you can directly calculate, copper loss, total copper loss, right? How will be S into air gap power? S is given 0.022 and air gap power we just now calculated. So it will be equal to 0.022 into 11.845. So total copper loss will be equal to 0.26 kilowatt. Okay. Otherwise, you could have calculated from I2 square R2. But to do that, I2 square R2, you need to calculate total current. That will be different from this I1 what we have calculated. That is why this approach is much more convenient. Otherwise, you have to make another equivalent circuit and then you need to find out how much current will flow in the rotor resistance. If you can see from this. Yeah, so how much current will flow in this side, that you have to find out. And that is not equal to I1, right? I hope you are getting it. You have to apply current division rule. And in AC circuit, applying current division rule or anything, it is a bit tricky or bit time consuming compared to DC circuit. Hence, at this stage of time, this expression will be very useful. Once you have computed air gap power, you can straight away calculate copper loss in rotor by nothing but S times air gap power. Another thing, converted power or mechanical power, that will be equal to 1 minus S times PG, right? So 1 minus 0.022 into 11.845, and it will be equal to 11.58 kilowatt. Right. So once you are done with air gap power, all the power you can compute straight away with this expression: SP S times air gap power and 1 minus S times air gap power. And finally, if you are asked to compute induced torque, or yeah, one thing is that induced torque. So let me now talk about torque related to torque. So induced torque or developed torque, what will be it? So it will be corresponding to this converted power. Developed torque is equal to converted power divided by rotor speed. Otherwise, air gap power divided by synchronous speed. Okay, we have both the quantities. So air gap power is nothing but 11.845 divided by synchronous speed is, we did calculate at the, so air gap speed is, or synchronous speed is 188.5. So 188.5 radian per second. And mind it, this is in kilowatts, so you have to multiply it with 1000. So that will give you 62.8 Newton meter. Okay. So you do not need to worry related to current, what will be the different current in rotor and all. It is good to know all those concepts because sometimes it will not be convenient to apply simplified version of concept everywhere. But try to reduce your time in you know critical examinations such as gate and all. Okay. So yeah, any final doubt in this thing? We will continue from this point in the next lecture. So any final doubt in this particular or till this thing, till this point?
No, sir.
Okay, great then. See you all on next Friday. Thank you very much for attending. Bye.
Thank you, sir.
Thank you.